This video is more of an academic thing. I'm not. There's going to be no builds or anything. I wanted to, discuss this, you know, circuit right here, um, which you see, in all like three-terminal regulator data books, and in various forms. But yeah, this kind of circuit, you see in practically every transistor data sheet. Um, Even the 317 has its variants in here. In fact, this is one, and the whole purpose of the circuit, if you're not familiar with it, um, is to, because these regulators are generally limited about an amp a piece, what they can supply. If you need more current than that, well, you're going to have to do something else. And curiously enough, the one thing you never see in a data sheet, is the idea of just, using some of these regulators in parallel. But like I said, hypothetically, um, it's possible. If you look at circuits like, like in the 317 here, they do just that in effect, using an op amp. I mean, they have three 317s in parallel, right? And those are adjustable regulators. So, but they have an op amp, kind of balancing the circuit, through a transistor, which actually controls the adjustment terminal of all three devices simultaneously. But, it stands to reason, if you can do this circuit, again, with the 317, you would need to do something kind of similar to this because it's an adjustable regulator. But it does stand to reason that they're using ballast resistors on the outside of that, to balance the supply from each regulator. So I mean, it stands to reason, that if you had some 7805s, that instead of having to go through and use a bunch of bypass transistors, like you see here, that you could just put them in parallel and put like a 0.1 ohm resistor, across the output. So at maximum current, you would lose a 0.1 volt drop on the output. But I mean, in theory, you could do this. I mean, there's really nothing wrong with doing it because these things self-regulate. But it's just that one voltage, because they sort of self-regulate, if you put a ballast resistor in the output, they're certainly not in the feedback loop. So, chances are pretty good that one regulator would be a little higher in voltage than another, and the theory is the regulator with the highest voltage might supply the highest current. So, but again, using a 0.2 ohm resistor, might alleviate that, but then you have a 0.2 volt drop. So instead of having a 5 volt supply, you might have a 4.8 volt supply, and it'll change. That voltage will change as they're loaded. But the only way to really be sure is to actually build it yourself on a test bench and have preferably 3 of them simultaneously supplied and measured simultaneously by 3 different amp meters, and that hopefully are close analogs, but have 3 different ammeters, on the supply you build. All right, and then take the same 3 regulators and change them out, because assuming that that nobody has 3 of the same ammeters, on hand, you can change them out to see if your current readings change. It gives you an idea how, if there's any difference between your ammeters, just to be sure. Because, you're trying to measure something that's rather a small voltage drop, okay, and the burden voltage of an ammeter will affect, quite possibly affect that output, and you don't want to do that. All right, so, so you can't just use one ammeter to do this at a time, move it from one circuit to another. You can't, because chances are pretty good whatever one you move that ammeter to might be the one that supplies all the current because it's got a burden voltage from your ammeter across it. So you got to watch things like that, when you're running tests. But yeah, if you had at least 2, preferably 3 side by side, and a big, like 10 of these things, you could change them out interchangeably and see what happens, with the various, again, start with a zero point 0.1 ohm drop resistor, and you know, play magical chairs with them, or the shell game with them, or something like that. Where you're constantly changing different devices out to see, to get just a little small statistical idea of what the things do. And if you're just going to use it in your project, you can do that. I wouldn't put that in production probably without extensive statistical verification, but I mean, in theory, it could be done. And again, it may not be completely balanced, but the question is, you got to remember these regulators are self-regulated. They got thermal shutdown in them and current limiting, so you're not likely going to hurt a regulator. And like we've established in previous videos, as long as the regulators have power applied to them, they can't sink current, they can only source it. So, like the 317, was a great example of that, on that video I did the other day, dropping that below the ground level, its output, and seeing what happens, but, I mean, in theory, these could be put in parallel, but, point is, if you can run at least a 2 ammeter test, you could probably get a good idea. You'll just have to do more changing out, and it's still not as good as a 3 one, because ostensibly you're going to want to, put 2 of them in parallel at least, right? Maybe 3. So, you got to take that shit into consideration. But at any rate, I did want to just mention that, FYI. And this right here is a current regulator circuit, and you could, current limiter, so you could, because these pass transistors have no current limiting at all. So your regulator may be safe, but your pass transistor can still get fried trying to supply a short circuit. So, so you put a circuit like this in here, and when the voltage drop across this RSC is high enough, it triggers this transistor and starts diverting current away from this transistor into your regulator, and it doesn't have to handle as much current as the regulator does. So typically they use a different transistor for this versus this. It's not as high power. You really just need to handle like an amp or so at most, just to get current flowing away from that. To overload the regulator is the idea, and the theory is the regulator itself will shut down, and that'll shut the whole circuit down in the event of a short circuit whenever it gets around to it. Depends on how much of a short circuit you're talking about, obviously, but but I guess it could happen quite quickly, in a high current, an actual dead short, if you got a low impedance transformer or something you're hooking it to. But at any rate, it's not a bad idea, and that's a much cheaper part. But anyway, I do have a little, like I said, a little thing I wrote, just to kind of test, some different ideas. I mean, and just to make an example, and I said, okay, we'll do a supply with a 7805. We want 3 amps out of our, power supply. We're powering it with a 12-volt transformer, because that's the one thing they don't really cover in these things, is the fact that trying to find a practical transformer. Again, you can do like a 6-volt transformer, with a filter cap and, bridge rectifier and stuff. Like a center tap 12-volt transformer, for example, you could use 6 volts across it. And with a single regulator, and filtering, you could probably get away with it. But you got to understand, this regulator has a 5-volt output, but it also has to have like a 7 or 8-volt input, and that's called the dropout of the regulator. Let's see. We got a 7805 here. Let's look at the specs of it. Come on. Let's see. So what's this for? It's 7815. We're not interested in that. Give me 50 million of these. Why don't you? Okay. Let's see. This is a new. I think this is a newer data sheet, though. It may not apply to the ones I have. So they may have changed the specifications trying to compete with more modern devices. Okay, yeah, it says input voltage required to maintain this regulation. So it's, at least 7.5. So there's a 2.5 volt dropout on this. so just assume 3 just in case, because some of these things will change with temperature and everything else. It's just safer to assume, there's about a 3-volt dropout. So, but they have that overhead, right? So, again, sometimes, with a regulator and a good filter cap, you can, because you don't want that when you have a ripple voltage, you don't want that trough to drop below, to drop down, this bottom part of your ripple waveform, under load, because I got this set to, 3, well, I got this set to like 4 amps on this. And by the way, if you want a link to this little this little Falstat circuit, it's right here, so just type that in. This 264XQC7Y, all lowercase. But yeah, like I said, this is running at 4 amps, but you want to make sure, that this bottom trough doesn't start going into your little overhead voltage zone, your dropout voltage zone. So you want to make sure this is always above that. Otherwise, it'll handle some ripple if there's some ripple in there, but it's still best if you want a nice clean supply just to try to keep it above that. So in other words, if this was in our situation, you want it no less than 7.5 volts absolute minimum, and but you really would like this to be this lower part of this waveform. You'd like it to be, 8 volts or so. But again, you can have some difficulty. You can just, you almost can't do it with a 6-volt power supply because, it's unloaded voltage is going to be like, coming out of the regulator is going to be like 8 volts or something like that. So, you're just, you're going to be lucky to do that, because that's what I'm saying. You'd have to use a rather large capacitor in it, and as a rule, it's, rough rule of thumb, it's 2,000 microfarads per amp. That's what I've always tended to use, although supposedly for surge rating and all that, you're supposed to go like 2 or 3 times that. But, I've always kind of stuck with that rule roughly, more can be better, but if you put too much capacitance, you can start really, you really increase your startup surge currents, and it's harder on the transformer and everything. So, but at any rate, but the fact of the matter is, to do a basic circuit like this, like I said, normally what you're going to end up doing is putting, because again, a 6-volt transformer, you can kind of do it, and as long as you're doing a light load, on it, you can. But if you have like a 6-volt, 3-amp transformer, and you're trying to drive a single regulator, forget all this booster stuff. You can't do that at all with a 6-volt. You can't. You are stuck with just a single regulator. That's all you can do off a 6-volt transformer. But again, you may have some ripple in it, it may be just unavoidable, depending on how big of a capacitor you put in there. But again, it can tolerate some ripple, but again, it's not going to be perfectly clean. So, in all likelihood, and the heavier your load, the more the ripple is going to start to show up in your output. So, and that's just with a single regulator. Again, forget all this transistor bypass bullshit. You can't do that at all with a 6-volt transformer and a 5-volt regulator. You can get away with a 3.3-volt regulator, but not a 5-volt. You're not going to do that. Although those 3.3 volts are kind of a different animal. Sometimes you need a 5-volt regulator to supply a 3-volt regulator safely, because they don't seem to have as generous specifications as these things do. And these can go up to 35 volts input. But any rate, in a practical scenario, most likely what are you going to do? You're going to use a 12-volt transformer, right? So, and that's the situation I'm mimicking here, is a 12-volt transformer under 4 load, and I, used, only a 4.7 microfarad or 4,700 microfarad cap here, because, just to see how it does, because in some schools of thought, you may be kind of almost better off with more ripple, because, in a circuit like this, you're trying to use a 12-volt power supply to, to power a, 5-volt regulator, I mean, really a lot of that's like wasted. So, you know, one school of thought is, maybe use a smaller capacitor than you need, because normally, for 3 amps, you want 6 millifarads at least, and this is close to that. So, this is a practical value, you might use it. So I just thought for shits and giggles I'd do it with this. But of course, you could do much larger than that, if you want to, especially for a circuit like this. So it's just, like I said, play with your own, in the way you like. But the fact of the matter is, okay, there are a lot of complications. Even just driving a regulator itself, you got to be, from a 12-volt supply, you do got to, crunch some numbers. It's not that the regulator's so much in danger, but, because it does have thermal shutdown and stuff, but trying to make sure you get full performance out of it, it can be difficult. And on my little worksheet here, my little example here, I assumed that for the regulator, I was going to use like a higher, a pretty low quality heat sink, like a person, 10 degrees centigrade per watt heat sink or so, like somebody might do. Let's read through the example first. Let's see. It said TJ Max. Now TJ Max actually is 150 degrees for these regulators. Even the 317, they just kind of recommend 125C. So, just for safety's sake, I'm using that, but, chances are pretty good, you can get more out of it. But some data sheets, I hunted forever for it, years ago for the 150 degree specification. I couldn't find it in any data sheet. Now you see them all over the fucking place, so I don't know what the fuck to make of that, but, 150C likely is their specification, so you can get a little extra. So again, you'll see different specifications on the thermal too. I'm using 5 degrees centigrade per watt because that's what's been all the data sheets I've ever used in the past. For these things, they have really lousy thermals. Although there's evidence, some of these new data sheets, that they may have actually improved that. Some of the data sheets I was looking at. So if you buy a new one, unlike the ones I have, you might actually get a little better performance, but it depends on who you buy it from, and not if you're going to buy it off Amazon, don't count on it. Anyway, but I'm assuming a 10 degree heat sink, 10 degrees centigrade per watt heat sink, so for a total of about 15 degrees centigrade per watt, and that includes, if you're just using a single heat sink, you don't need thermal pads on it, so you just need heat sink grease, but a rather light coating of heat sink grease. Don't make the mistake a lot of people do and put a thick coating of heat sink grease on your part. You're better off with a thin coating. Less is more, and it doesn't have to be like super thin, but you don't want a thick coating on it at all. You want it to where you can kind of see the metal through it overall, and just put a little extra on top of that. Basically you should, rub it around with your finger and just kind of rub it off, until there's just a thin coating on it, and then maybe put a little dab in the middle, just a small little with like a toothpick or something, and before you, press it onto the heat sink, that should give you enough heat sink, grease. You don't want more thermal compound on it, than absolutely minimally necessary, because again, heat sink compound does not have really good thermal conductivity. The thicker it is, the more you degrade your thermal performance, and you don't want to do that. In fact, that'll kill your part, if you get carried away. Less is more when it comes to heat sink grease, believe me. But at any rate, 15 degrees centigrade per watt thermal, will be our total operating parameter. Okay, so, basically, assuming 125C operating limit, I'm trying to operate it, I said at 50C, but actually I changed that to 40C. I just forgot to change it in the notes here. Yeah, because I actually changed it to 40C for the rest of these calculations. In fact, I'm going to change that because I forgot to. Oh, God, I hate Adobe. Oh. Man, they just fuck this program up, like, every time they force it on you, you can't go back to an older version of it. I just, Adobe just has their head up their ass. But yeah, so any rate, it's actually going to be a, a little bit, bigger of a range than this. But at any rate, just running with this. This is an error here. Just basically, saying that with a 15 degree centigrade per watt, because in practice, we'd have an extra, in fact, basically I did it up here, okay? This is my spreadsheet, and for doing thermal calculations on transistors, and it's a really simple spreadsheet, but it does apply here to regulators too. It's any device that the thermal specification, degree centigrade per watt. All right. Let's see. God damn it. Stupid fucking crap. Any rate, that, and it's TJ Maxx. Okay. Those are the only two figures you have to enter into this spreadsheet, really. All right. So you got this number here, for example, in this transistor. That's a degree centigrade per watt out of a data sheet. And if you read my note here, you can find the degree centigrade per watt off of a typical transistor data sheet. Like this is the transistor I've got in my little note here. You can actually find so that we're using in our example. This is a transistor, the MJ2955. But you can find the degree centigrade per watt by simply looking at this graph if you want, and you see that this is a 75 watt part. That's what it's rated, and that it has 150 degree temperature rating, and that it, of course, is specified for 25 degrees centigrade at 75 watts. So you take 150, subtract 25 degrees from it, that's 125. Okay, so that's how many degrees, 125 degrees, and you divide it by 75 watts, and that'll give you your figure of 1.667 or whatever in this case. See, here in this data sheet they actually do specify it, but some data sheets they don't, and this is the figure: thermal resistance, junction to case. Okay, that's what you're looking for, 1.67 degrees centigrade per watt. And sometimes they're elusive in some instances, but that's an alternate way to get this figure. So and you can see it here. I've got the MJ2955 here that I inserted. I've got zero inventory of it. That's one of the reasons I'm not doing any builds for you, because this really is the best transistor for the job, but I could possibly use a TIP42, although the ones I got of those I bought off Amazon, so they're probably not the real thing, and they'll probably blow out on me, at half the ratings if I'm lucky. So I really don't have that many PNP transistors in my inventory. In fact, this is my entire inventory of transistors, and I have used several of these since I created this list. But at any rate, right up here, on my spreadsheet, I do have a specification for the voltage. Okay, so it gives us the voltage drop. It's just really just that by that, and I'm not going to explain to you why I have that. Just this is the important figure right here. Is that's the voltage drop across the element, and that's the voltage drop across the collector emitter, and a transistor, BJT. So, and here's our operating temperature in degrees Celsius. Okay, and that 40 degrees equates to 104 Fahrenheit. And this is the heat sink thermal properties. Now, just like a transistor, heat sinks have a degree centigrade per watt rating too. However, understand this, and that's part of the little note I made up here, which you may want to kind of check out, which I talk about, the heat sinks are not just chosen on degree centigrade per watt, they're also chosen on, thermal properties. The best thing to do is to pull up a data sheet like this off Mauser, and some of these heat sinks, and just to show you, let me widen this out. See, Motherfucker. Son of a... Ugh. Anyway, God, I hate Microsoft. You know, them and their fucking arrows trying to resize things, you know, and half this shit, you know, you spend 20 seconds trying to get a fucking proper resizing arrow to pop up. It's just fucking ridiculous. But at any rate, you know, you won't see a wattage specification for these things, but you can see the thermal resistance, you know, 1.5, 1, you know, so, you know, for a pretty decent price, you know, you can, but these aren't appropriate. The thing is that, you know, this heatsink right here has, you know, like 1 degree centigrade per watt, right? But if you actually look at the data sheet of it, you know, you end up realizing that, you know, geez, this thing, you know, you're going to be lucky for it to handle 5 watts. Let's see if it even has a curve. And see, this one, you know, they're being coy with it. They won't even tell you any. This data here is like useless. One of the most useless data sheets I've seen on a heatsink. But what you're looking for is, you know, a heatsink data sheet, you know, that has curves in it similar to this. Okay, and you can see, okay, this is for a TO220 or something like that, but you can see that it says heat dissipated in watts, and it maxes out at 10, okay, but you can see the arrows here. This curve here applies to heat dissipated in watts and its temperature rise. This one here assumes that you're, you know, using forced air cooling, and it tells you what its thermal resistance is with forced air cooling. And most of these heatsink ratings, you know, are based on forced air cooling. So when you see, you know, like 1 degree centigrade per watt, that's usually with forced air cooling. There's no way you're going to get that without it being a huge heatsink, you know, just sitting there with no airflow across it, just using, you know, convection to cool it. But, you know, so you can use this curve, you know, if you're going to use a fan, but if you want to use it without a fan, you can use it here. But you see what the temperature rise without a fan is. You can totally ignore these axes for this forced air curve. They don't apply. The only axes that apply, you know, to these two, you know, is when you're just using it with no forced air. So, but it tells you how much the temperature is going to rise for a given amount of wattage you're trying to dissipate. But you can see, like this particular heatsink, it's only rated up to 10 watts, but shit, by the time it gets up to here, you know, your components probably had a meltdown. You know, it's 100 degrees centigrade. Maybe not, though. I mean, you know, again, it depends on your component. But this heatsink is still only specified to 8 watts. You know, and again, if you looked at some of those others, you would realize that they are only specified to, and I'm probably going to make this a 2-part video because this is going to be kind of lengthy. But these are only specified, you know, like a little heatsink like this, you're not going to be able to put 50 watts through it. You know, the damn thing, I mean, you can put 50 watts through it, but, you know, if you don't mind your component being like 400 degrees centigrade. So, you know, so you got to use, there is a relationship between the size of the heatsink and the thermal resistance. You can't just look at thermal resistance alone, but that thermal resistance is all you need for these calculations up here. So, you know, because they usually don't have a wattage rating on these heatsinks, not that I've seen from suppliers anyway. I mean, there's just no wattage rating that says, you know, hey, this is for a, you know, a 20 watt part, you know, because, again, the wattage we're looking at dealing with here, you know, in our example is, you know, like I said, with 3 amps at 10 volts, you know, we're looking at 30 watts. So, you know, that little heatsink we're just looking at would be woefully inadequate. And there's really no telling, based on the forced air cooling diagram, you know, how many watts it can sink. So if it lacks, you know, if it lacks this diagram, like that one heatsink I pulled up didn't have it, you know, then you have no idea what the actual thermal performance of the heatsink is. You know, again, that one I pulled up and closed said that was bullshit. You know, since they lack this curve, you have no idea, no reference to say, what's going to happen if my fan breaks? You know, that kind of thing. But it more importantly, it gives you an idea of how many watts this damn thing can actually handle with no forced air cooling. It's a critical fucking part to have in your heatsink chart. And this thing is like a fucking catalog of heat sinks. There's a lot of different heat sinks in here. Just from this one catalog alone, if you can get it off Mauser, it's the board level Wakefield catalog, which is the same people that did that last sheet, but they failed to have that data in it. But yeah, there's a lot of different heat sinks in here, and the further you go down, see, this one can only handle 5 watts, for example. You probably wouldn't want that, because even under forced air cooling, I guess you can sort of ignore that, because it does show you, what the thermals are and how they increase with lower fan speed. But the thing is that you can't take a tiny heat sink like this, okay, and dissipate 50 or 60 watts. I don't care how much forced air cooling you have. Like I said, if you want to dip it in a, take it out on an adventure in Antarctica, you're probably in good shape. But, the fact of the matter is, for an average situation, no, you're not going to want to use a small heat sink like this for a large amount of power. So that's why having a graph like this and saying, well, this part is technically designed for about 5 watts, even though I'm sure you can get more than that out of it. It shows you what the consequence is, for going above that with no forced air cooling. But beyond that, if you're in that range, you could probably get away with it. Like you could probably take this out to 8, maybe even 10 watts. But maybe, how expensive is your part? I don't know, but you can run your own thermal tests on it and stuff and see. But that's rather involved. But at any rate, that's a little dossier on on fucking heat sinks for you. So usually thermal conductivity is advised, and forced air cooling, I've just kind of covered all that. And we'll get to that later. These are alternatives, alternative ways we could do it to the way I'm discussing, just some ideas. And you'll see the need for them later. But yeah, so if you take this, this regulator, all right, and I put thermals in it, right? Okay, here I assume 15 degrees centigrade per watt. So, and let me finish the spreadsheet in case you're wondering, because you can do this yourself. It's real simple. Like I said, here is just a value. Well, actually, here, let's do it for the regulator. Here is, of course, the thermal, 5 degrees centigrade per watt. And here is the TJ max, which is, again, what they actually specify. In fact, I will use 125, because that's what I used in my example. And I'll even use 50 degrees, like I used in my example. Okay. And so that's giving me, 50 degrees. And this is the practical watts. So at these specifications, this is the amount of wattage, it'll dissipate. And this is the maximum current it can run within that specification. So in other words, we could only really get, about 0.8 volts, with a 10 volt drop across it, which is what we have, 14.82 is, looking back at our full stat circuit here, it's like I said, you see that, the peak up here is, wrong graph. Yeah, the peak up here is 14.6 volts here, but I'm at 4 amps, 4.1 amps on average. But see, if I lowered it, to spec, this isn't the exact one I used in my sheet there. Let's see, now I'm to 5 amps. Damn it, I went the wrong way. Oh, come on, it takes it a while to adjust. Shit. I think this is an older version of it or something. Yeah, that's about right. But yeah, you're roughly 15 volts. Speed it up just to make sure it stabilizes. Okay. Yeah, you're, roughly 14.8 volts, right, at 3 amps. At roughly 3 amps. So, and the minimum, of our drop is 11.1 volts. So, so that's well above our dropout of 7.5 to 8 volts that we talked about earlier. So, all right, there you go. but then of course our average is 13 volts. But again, usually you got to look at the extremes. So just to be safe, I mean, you don't want this to blow. You don't want that series pass transistor to go short circuit on you because you overheated it and it failed and then cooked your circuit with like 12 volts when it's only expecting 5 volts, do you? So again, even with this design, I'm being rather risky. So just to let you know, I'm being rather risky. It doesn't have the safety margins I normally want to see in a circuit. But at any rate, for our little sheet, basically, that's why we're looking at 10 volts, because it's got roughly 15 volts minus 5 volts, so that's a 10 volt power voltage that, worth of power it has to absorb. 10 volts at the current, that the thing's supplying, which in this case is 1 amp, if we're lucky, but it actually can only supply 0.8 amps without violating its thermal specifications. Now, of course, with this regulator, it'll just shut itself down if you try going up to 1 amp with it. At some point, it'll shut itself down. A lot of times, those aren't immediate. Those thermal shutdowns are not immediate. If you look at the data sheets and study them, you realize it can go a little above its rating, before it thermally shuts down, usually, but it depends on temperature and everything, so. But anyway, for our examples, that's what I'm kind of assuming, and that's why I just said, basically, I'm just going to, assume that it's like half an amp, right? That's a nice safe figure because, you really want your pass transistor doing most of the heavy lifting. But, it's okay, if you can get away with it, to use it higher. So, in fact, maybe even preferable. But I'm just trying to, give us some wiggle room here. Even though, like I said, I probably would be better off with, assuming higher current through the regulator. But at 50 degrees centigrade, you're kind of limited. But again, if we back that off to, 40 degrees centigrade, all right, then we're, at 1 amp now, so, it's not a huge problem. But at any rate, how this spreadsheet works, you can ignore all this stuff. This is just garbage that I copied in from previous tests I ran. It's not calculations or anything for the most part. I mean, it sort of is, but anyway, this is just thermals I wanted to save from experiments I did in the past, for the most part. But here, like I said, these first two numbers, all right, are, just numbers you type in, all right, and these numbers up here, as I showed you, are just numbers you type in, 3.5, 40 degrees for the temperature, that's for the heat sinks, thermal, that's for the temperature, and that's for the voltage drop. Again, you don't have to base it off this crap. You can just type it in directly in there if you wanted to. These are all calculated fields. So you see, this right here is just a repeat of our thermal, all right, and this right here is just a repeat of our temperature. It just, copies the same thing, clear on down from these two columns, right? So that's nothing fancy. In fact, you could just type this data directly in here if you just wanted to do a single version instead of having a whole inventory list like I have here that I did it with, so I can compare all my transistors side by side. So anyway, you got that, but then the practical watts, now that has an actual formula, and you can see what it's based on. Basically, you can see it's, F96 minus H96, so there's F minus H, so it's taking the maximum TJ max and subtracting the ambient temperature, and then it's dividing that by the quantity of the sum of G, which is our thermal degree centigrade per watt of our heat sink. And this is just a heat sink only here, by the way. You know, remember, this is the thermal of our device. This is the thermal of our heatsink. So, but basically, it's adding the thermal of our heatsink to the thermal of our device. So it's giving us our total thermal resistance. Now, in the heatsink, I'm also, assuming, you know enough to, to take into account any, like, heatsink grease, or, if you use them, electrical isolators, because sometimes you need them, sometimes you don't. It depends on what you're doing. I mean, sometimes you can get away without the insulators. It's always best to get away without them if you can, because that's an additional temperature drop. It's an additional thermal resistance, in your circuit, and you want to minimize your thermal resistance. But anyway, it's a simple formula. You're basically just trying to find the temperature, across the device. So if you got, like if the TJ max is 150 degrees, all right, and your ambient, is 40 degrees, well, you got a 110 degree temperature difference, right? That's your operating temperature range that your heat sink's got to work over. And so you're basically just dividing that temperature range by the thermal of your device, added to the thermal of your heat sink, and heat sink grease, everything else, is included in this. So, so you get that sum, and that gives you this output. That's your practical watts. That's how many practical watts you can actually get out of the device. So like in one of these transistors, like a TIP42, it's rated at 65 watts, but you can't get more than 20 out of it. And that's with a halfway decent heat sink. That's not a terrible heat sink right there. But you can't get more than 20 watts out of it. In fact, the only way you could ever get the wattage that a transistor is actually rated for, is if you actually have its case at room temperature. That's what it's rated for. Its case has to be at 25 degrees centigrade, period. Which means in an actual room that was at 25 degrees centigrade, you would have to have that thing in a refrigerator, to actually do that, to keep its case actually at 25 degrees, because the thing's going to heat up. And so when you touch it, it can't be any more than 25 degrees. Now its junction is going to be a lot hotter than that. In fact, if you're running 65 watts through that thing, its junction is going to be at 150 degrees centigrade. That's how hot the chip itself is going to be inside that thing. But the case has got to be cool enough to touch. That's the only way you're getting 60, way more than cool enough to touch. That's the only way you're going to get 65 watts out of this particular transistor. They are specified at 25 degrees centigrade, which, like I said, unless you're using some kind of chiller or something, you could have a water chiller, right, on your heat sink, and then actually have a bunch of Peltier devices chilling the water itself, down to the point to where it'll keep that temperature at 25 degrees centigrade. That's the only way you're going to fucking get that. And the Peltier thing, that's way trickier than you might think. So that's a whole other video worth of information there if you start thinking about that. Because Peltier devices generate their own heat, okay? So you got to get rid of that, plus whatever you're trying to heat sink. So it's really not a good idea to bolt the Peltier, our device right to a Peltier device. It's better to kind of do it sort of off-site, like in a water bath, for example. But anyway, but roll your own. Because like I said, you might get some benefit. Just you're up to your particular scenario. But anyway, to finish up the spreadsheet, like I said, we had that calculation. Then we finally have this calculation, which is really just taking our result, from the practical wattage and dividing it by our voltage drop. All right, so that's how I figure out what your amp limit is. So it's real simple. It's just a real simple little calculation that you can, easily, do it yourself. For all your components, like I did here, and you can compare them side by side, and you can either, enter just components off the internet or whatever, and kind of, just quickly compare what the component can actually do, okay, based on the heat sink you can afford. Now, like I said, you don't have to buy heat sinks either. That's one of the good things about having a catalog, is that, purchased heat sinks are better because you got specifications and everything else. But let's say you're on a budget, or you're on a budget, and you don't have $50 to buy a heat sink with. Because like I said, some of the bigger, more The heat sinks that can handle more power are obviously more expensive. If you get down here, for example, you see some of the heat sinks are rated at 20 watts now, right? Further on down the catalog, and you can get an idea, for the A figure, it's that's the height. All right, so 2.5 inches is how big it is, and then you got a little over an inch. That's not a terribly big heat sink. That probably wouldn't be super expensive, but it's rated up to 20 watts, and then some of these, is rated 25 watts. Um, this thing here is rated to 50 watts. And these heat sinks are, let's see, 3 inches by, well, this is 4 inch by 3 inch, so by 1 inch depth. So I've had some heat sinks like this. They're pretty good little heat sinks, actually. Awesome equipment, That's what's good about, if you can find equipment to salvage, you can get things like heat sinks and stuff out of them. Old stereos, that kind of thing, they can be worth their weight in gold. Pick up a stereo at the thrift store for $5 or whatever, and you get a $20 heat sink in there, a $50 heat sink. But at any rate, let's see, these are rated at 50 watts. So my point is that data sheets like this can give you a feel, for what heat sink sizes are and what their performance is, and then you could just take your own scrap aluminum, okay, and just cut your own. All right, because if you take a block of aluminum that's like a half an inch thick by 4 inches by 4 inches, it's going to give you similar capabilities and probably better capabilities than this, but it doesn't have the fin. So you could take a heat sink like this and mount it on top of that and make a whopping more powerful heat sink. So you could combine two heat sinks, and since they will have a bigger contact area, I mean, it could make a piece of aluminum block, really respond well to forced air cooling. But you can just take a piece of aluminum, and people have made their own heat sinks. You can take aluminum sheet, the OED aluminum sheet, and you may not know this, but aluminum is actually really easy to cut. If you have a circular saw and you just put a regular plywood blade in it, preferably one that's carbide tip, but it can be a dull blade, and you just cut through that shit like butter. You won't believe how easy it is. Be careful, because it will kick if you're not, be careful when feeding it in particular, because it will kick and it will throw chips, little aluminum chips everywhere, which is good to wear some pants, because it throws them some force. But I've cut through, 2-inch thick aluminum slabs with a circular saw before, believe it or not. It's amazing how it's almost fun to do. It's unbelievable how easy it is to actually cut through aluminum. I mean, I've got lots of aluminum parts I've cut through that way. You can cut through thick, but the thinner, the more likely it is to vibrate. But still, I mean, it works. But definitely wear goggles, because again, it will throw little metal turds everywhere. So, but yeah, you can make your own. Just go to your local steel scrap yard, see if you'll. A lot of times they'll let you rummage through their scrap bins and stuff, and sell you what's in there. You can find some good shit, at your local steel yards, that deal in reclaimed metals. So, it's you can find some really good shit that way, if you just think outside the box when it comes to heat sink. Now, of course, you don't know what the thermal ratings are, but you could kind of run tests on your own with a power resistor. Again, mount your detector. Maybe preferably drill a hole in it if you can. Mount a little thermocouple inside of it so that radiation from the resistor doesn't heat it up. But you can kind of see what the temperature rise is, for a known amount of wattage. So you can put like 10 watts in it or 20 watts with it if if you have a bigger resistor, or mount 2 of them or whatever on there. And you kind of see how much the temperature rises. It'll give you a clue what the thermal properties are. So, if you could, especially if you could apply your theoretical power to it and just measure the temperature in a kind of a controlled way without actually having to put your device on it, it'll give you an idea of how to characterize it. So, if you're that concerned. But anyway, the fact of the matter is, it would be a good idea to make a heat sink testing piece of test equipment that tests heat sinks. Honestly, I've been kind of curious about doing that for years. But the point is that you can, this helps you with heat sinks. And again, the bigger the better. I mean, honestly, if you took a fucking engine block, okay, and attached your device to it, you're probably not gonna have to worry about it overheating. So, be the king of overkill, although maybe not to that extent, but you just be the king of overkill, and you'll probably be all right. Now, again, with a regulator, again, this actually has a really good, heat sink where we have it right now. So like I said, I set it to 3.5 degrees centigrade per watt as opposed to the 15 I specified in my notes. So, if you look at that, if I put it to 15 degrees centigrade per watt, even with a 40 degree temperature rise, you're going to be lucky to be able to get the half an amp that I talk about in my little design sheet here. Because I'm assuming 500 milliamps based on these parameters. So, in fact, I probably did change the temperature. I just forgot to actually put it in there. Forgot to update the things, update the text. But yeah, I mean, it's like I said, no, you'd be lucky, under these conditions, and that's with a 10-volt drop, etc. And with 125 degrees centigrade, you'd be lucky to even hit half an amp. But since it will work at 150 C, and it is thermally protected, yeah, you can get the 500, with a little bit to spare at 40 degrees and 15. And again, that's powering it off a 12-volt power supply, So, that's the reason I have, because normally I would enter, like, in our case, like 15 volts and an output of 5 volts, and that gives you the same differential. That's why I have that way, even though it's unnecessary, but that's why it's there. Because we have 15 volts input, 5 volts output, and what the pass element has to deal with is what's in between. So, but again, in our case, yeah, we can use that 500 milliamps, but no more. Not with these thermals you can't, not with 15 degrees, but this is the kind of heat sink, a 10 degree heat per watt. Well, actually, I'm wrong. It's a 10 degree heat sink. So, no, we're okay. I just, yeah, I forgot that was already taken care of here. But yeah, so we can do 700 milliamps, okay, under these circumstances. But there will be circumstances if you're driving it off a higher voltage, which you might be, where you're going to really be in a boat like that. But if you use a really lousy heat sink, 15 degrees centigrade per watt actually is a good, because this is what most people might just find in their junk bin, a little skimpy heat sink, and attach it to that. Well, yeah, you're probably going to be looking at a 15 degrees centigrade per watt heat sink. So, because they have heat sinks, all over the map, just go to Mauser and, enter heat sinks, and, like I said, the thermal resistance, you can see, can range from anywhere from 0.1 degrees centigrade per watt, which is an amazingly big heat sink. They sell them 10, 12, 16, 19, 32, 64, 100 degrees centigrade per watt. I mean, that's awful. 100 degrees centigrade per watt. Let's see. Thin style. Come on. Let's see. We want to mount. Not dip. TO220. Where's TO220? TO220. Here we go. TO1, TO. Yeah, we'll go with this. Fuck it. We're mostly interested in heat sinks for these types of components, but it's informative to look at the others. But so again, and that's with no fucking $167 is not their cheapest heat sink. How many did they return? 8? Bullshit. They don't have just a 8. Ugh. It's aggravating. But at any rate, again, they got such cheesy heat sinks. I mean, it's spring. What's that have to do with? That's a heat sink part. But, like a little, you might tack something like this on here. That's for a TO220. 27 cent, cheap little heat sink. 25 degrees centigrade per watt. What are you going to do with that? 25 degrees centigrade per watt. That is not going to do shit. Let's put 25 degrees centigrade per watt in a little spreadsheet and see what it does. That's for the heat sink alone on top of the thermal. Okay, that means with your TO220 in this circumstance, you can only do 360 milliamps. So that's what it's going to get you, you know, if you just take some little cheesy heat sink and put on your box without doing calculations like this. You know, so the damn thing's going to be crapping out on you at way less than the current you expect, and you won't know why. Why? Why does it keep, you know, stopping? Why does it keep shutting down? You know, now, you know, if you did it at 10 volts, like you could get your hands on an 8-volt transformer, so you could actually properly power a 5-volt power supply, then you could actually, you know, with that same heat sink, do 700 milliamps. So that just goes to show you, even if you had, because again, we got a 5-volt voltage drop in with a ripple and everything, that's the best you're going to really be able to do in practice. You're going to have a hard time doing better than that, really. You know, but you're still going to be limited with a heat sink like that. Yeah, no, that's going to suck. Donkey balls, big time. You know, but at 10 degrees centigrade, you know, you're fine. In fact, if the thing could handle 1.4 amps, you could do that at this voltage drop. But at the voltage we're working with, well, guess what? You know, we're back to 700 milliamps for our example. So it's 0.7, but again, we're going with 0.5, especially if you wanted to run it at 50 centigrade, which is where I did actually do my calculations after all, even though I said I didn't. So, anyway, let me pause here. Yeah, but, you know, I wanted to say that, you know, I used a pretty lousy design here on the regulator because I wanted to emphasize the transistor, which is what we're really trying to do, right? We're trying to get a transistor that passes more than 1 amp of current out of it. But like I said, you know, if you wanted to use, you know, a good heat sink, you know, like 5 degrees centigrade per watt, you know, you can get your 1 amp out of it. And by the way, I wanted to cover ambient temperature just in a nutshell. You might want to watch the video I did a while back about ambient temperature. You know, what is ambient temperature? Where I discuss this at length. But in a nutshell, you know, it's just got you little fucking gnat. You know, in a nutshell, ambient temperature is not the temperature of your room. It's the temperature inside your enclosure, right around your device. You know, in fact, you ought to measure it, you know, just right below your device, actually, you know, and upstream from any forced air cooling you might have. So, but yeah, if you want to use, you know, remember, you know, to get a 5 degrees centigrade per watt with no airflow on it, you're going to have to use a big heat sink. But you're only dissipating about 10 watts. It's 1 amp, okay, at 10 volts drop across it, right? So it's about 10 watts you got to, you know, you got to deal with. So if you're going to purchase a heat sink, you know, again, rewind the video a little bit and check my discussion of that. But you know, with forced air cooling, it's pretty easy to find a heat sink that's 5 degrees centigrade per watt. Okay, if you're going to buy one, if you're going to make one, you know, make it extra big. Big king overkill. But ambient temperature, you know, like I said, is the device, you know, is the temperature right upstream from your device in forced air cooling, or right below your device. You know, I'm talking like, you know, within, you know, half an inch, quarter inch preferably. You know, will start to give you good ratings, but it's free air. You know, it's not necessarily the temperature of the heat sink, but it's right around your device without touching anything. So that's your ambient temperature, you know, that you got to use. So don't just think, hey, it's just, you know, going to be, you know, no more than 30 degrees centigrade, you know, in my building, you know, okay, I can use that. No, you can't. You know, it's right in your device. Even if your device isn't in an enclosure, you got to do this, because it still will be locally hot, especially if there's no forced air cooling. So even if your board's just sitting out on your bench, you know, you got to take that into account. It'll be probably significantly less than 50 degrees, but it could still be hotter than you think, depending on what other components are generating heat in the area. So it's still the ambient temperature right around the device, you know, really within a quarter of an inch. Again, preferably below it, because you don't want to get in the heat plume of the device, especially if there is no forced air cooling. So just in a nutshell, you know, that's what ambient temperature is. So again, this stuff is more complicated than you might think. This is actually one of the more difficult challenges, in basic electronics. If you're actually trying to build a little power supply like this, it's there's a lot of things that you can do wrong. But for a regulator, at least it does have its own limiting built into it. A transistor doesn't. So, and you can see down here, the transistor we're going to use is this, right? In my example, that can only handle 1.4 amps, with these same specifications, 50 degrees, 10 volt drop. But, for my design, I had to roll it back to 40 degrees because I just couldn't get acceptable performance out of it otherwise, without having to have a ridiculously high heat sink. And even as it is, we're going to certainly have to have a heat sink. I'm basing off 2.5 degrees centigrade per watt heat sink, which is doable, and I, showed you in Mauser, there are a lot of heat sinks that aren't, too bad of a price. You can get one with forced air cooling, and again, that's the only way you're going to get a cheap one is rated forced air cooling for something like this. But that gives you, 2.5 volts degrees centigrade per watt. That again includes your heatsink grease, so you're going to need a heatsink that is rated like at least 0.2, 0.3 degrees centigrade per watt below that. So you need a like a 2.2 degrees centigrade per watt heatsink, and then that gives you a little bit of breathing room with your thermal conductivity. And again, as long as that's the only device mounted, like your regulator, for example, is the only device mounted on that heatsink, that's all you have to worry about. You don't need an insulator pad. If you need an insulator pad, then you got to take that thermal resistance into account too, which could be another degree centigrade per watt. In worst case scenarios, especially with like those silicon pads. Generally, avoid silicon pads unless it's just a real you're not dealing with a lot of power. You can kind of get away with those, but generally avoid those. Go with the mica insulators. They're cheap. You can buy like a whole bag of them for, if you do some digging on Amazon. I bought a whole bag of them for like $5 or $6, and you get them off of eBay, and that was like for 50 of them. So you can get them off eBay too. In fact, if you need those little nylon insulators, I found a good place on eBay to buy them, and it's domestic too, in the USA, and they were like $250 for like 50 of them or something like that. In fact, I can go try to show you that. Hold on a second. Okay, this is some of the shit I bought on eBay, by the way, so you might, if you're in the market for some of these, like an adapter, this is, one of the deals I found. This little DAC module, which is, 12-bit, 165 megasample for $19. I bought some of these ZAR 2206s. I hadn't tested them yet, but, it came with like, I bought 2 of them for $3, so that's not too bad. I bought one of these little boards for the Nano VNA, and bought some of these sockets, but it wasn't a collection of sockets, so it's just one for, in case I wanted to, make my own boards for the analog discovery. So, I needed a connector like this for it. So, and I bought these BNC connectors, 10 for $5. That you can actually find, you buy like 25 for $9 or something on Amazon, which I bought some of those too. BNC connectors are one of the better choices, believe it or not, if you have a lot of shit like that. I bought that for a different project. It's a fast TF card reader, so I can hook it up to an ST and have high data rates. So I can use fast SD cards, for an STM processor, like on a Nucleo board. So I could dump data, from an ADC, if you're doing data collection, to an SD card, a multi-gig, SD card. So, but you can do it fast with this module, but it requires a module like this. Let's see, some cables, and that's where I bought my Seek thermal camera. Here's where I bought the hand tech, and here's where I bought my hammer tech. Here's where I bought one of those little things. My credit card wouldn't let me buy anything off of, AliExpress or anything. So, and for half the vendors, anything in Canadian dollars or whatever, I mean, it won't let me do it, fuckers. Um, Dummy batteries, so you can make your own battery eliminator. This is a really good deal, $11, and it came with like 24 of them. And here are those little insulators. Here's where I bought my analog discovery, by the way. So, and here I bought this little, generator module, which I covered in one of my videos for like $30, but it's cheaper than the one on Amazon with a bigger screen. On that little resistance meter, I bought milliometer. Excellent little meter, although half of it's in fucking Chinese. There's no way to convert it all to English, but still, it's an awesome little meter. I bought a blue laser diode, which actually is blue. And here's where I bought my function generator. And here's where I bought my O1 meter, so, used. And here's where I bought a Tesla coil top load, for really cheap. So, I assume you can just enter these numbers. And here's where I bought another thing for my Tesla coil. Here's where I bought the coil for my Tesla coil. And here's where I bought a little LiDAR module for $25. That was awesome. And here's where I bought, Microsoft Office in, 2010. That works great. Here's I bought a little microchip PIC-Kit 4 programmer. Here's I bought a X-ray tube, not really an X-ray tube, but a tube you can use for X-rays. Here's where I bought my little RF Explorer thing. Here's where I bought the Tesla coil driver board, and this is me trying to buy a top load from this guy, which was apparently dicking me around, so I canceled the order. This is a radiation test card for a radiation meter. This little robot I bought, complete with servos, for $55. Excellent deal. This is for X-rays. A little X-ray cassette. These are actually fucking hard to find if you don't know what you're looking for. If you're into X-rays, if I ever actually build that shit up, I might look into it. And this is an actual X-ray tube I bought. So, and this little scope, I bought, and this is where I bought the 3018 Pro a number of years ago, complete with laser and everything. It was a decent deal. But going back to the, thought you might find that interesting, because I found some good deals that took lots of hours of exploring. Shit. Come on. Okay. Here we go. Okay. So, yeah, let's see if these guys are still around. See, it's like 99 cents. All right. And again, it's, it's not free shipping. So, oh, these are from China. That's interesting. They didn't used to be. This was handled by somebody locally when I bought it. But, okay. But at any rate, these are the, the little, for TO220s, if you do need to use insulators, this is where to get them. So, you try to get shit like this off of Amazon, and they're going to try to charge like 20 cents a piece for these fucking things, if that cheap. So, and even from Jamico or anybody, these things are just, you can't buy them individually, but, if you know what you're looking for, and it's got to be these exact ones, because, on Amazon, you'll find a lot of these on there, but they're the wrong dimensions. So, you got to look at the dimensions closely, but these motherfuckers actually work. So, it's by these people, I suppose. And even though when I bought them, again, I bought them, they came from somebody in America, and they got here really quick. They sent them in an envelope. So, just a paper envelope, not a padded envelope. But, man, it was a good deal. So, but they're out there, but you got to look for, search for something like this. And it's got to have the TO220 in it, to try to find it. But yeah, I mean, these guys apparently sell it. But like I said, it cost me $3.95 with shipping and everything, and that's where to find those insulators if you need them. And again, For the most part, you may not need it on this, but you might. It depends on if you have something else bolted to your heatsink or not. So then you'll need these in an insulator. And believe me, I tried coming up with like, clever alternatives to these by like buying some, you know, like silicon rubber tubing, right? Okay, and trying to cut that into little little links so it would insulate my screw from the deal. And you can use nylon mounting screws, which I've done in the past, but but since you're dealing with a lot of thermal issues here, there's a possibility for one, they could melt and they could weaken, but they could break off, because nylon still isn't that it's not that difficult to break the head off of it. And if it does, your device is going to become detached from the heatsink, and then you're screwed. So it's generally not the best idea to use nylon. Nylon is still a thermoplastic; it will melt. But at the very least, it can come loose, as it goes through thermal cycles, and it causes the nylon to expand by it partially melting. So even if it doesn't break off, it still may become loose, and then still your device isn't making good contact with the heatsink, so you're screwed. So you're still, really, you got to do this, but don't do the tubing thing. That was the biggest pain in the fucking ass I've ever gone through. Trying to use a little piece of silicon tubing on there. Yeah, so that was a big pain in the ass. So don't do that. If you buy heat sinks, some of them will have clips in there. A lot of those heatsink designs are based on thermal clips. This one certainly doesn't have that, but I mean a lot of these actually do. So, you just gotta, do your own research. Hey, what was that? Here are some nylon little deals. Okay, 23 cents a piece for those same washers. They do sell them on here, and you can buy 10 for 22 cents a piece. So, I'd much rather buy like 50 of them for that same couple of $2 or $3. You know what I mean? So, but again, sometimes they do have the heatsink clips and things like that. So, just do your own investigation. But they do have heat sinks that don't require any kind of thing like that. But again, they're individual for individual devices, so you don't have to worry about isolating the component. So, but I got a number of them that just slide onto the device. But again, they're going to be low degree centigrade per watt. But anyway, one of the points I was trying to make with this is that you can get your regulator to perform up to its 1 amp rating just by using a suitable heatsink. But it's not the point of the video. But and certainly my advice would be, instead of because again, doing this design, I just wanted to use a pretty lousy example just to kind of show you some of the difficulties, but mostly focus on the transistor part of it, because that is more challenging. And like I said, but I got to use 2.5 degrees centigrade per watt heat sink, and again, better than that once you account for the grease. Then you got your 10 volt drop, and then you got your 40 degree design temperature, and that allows me to get to about 2.6 amps. And even with a TIP42, you could almost do it, but 2955 as a 10 amp rating, but it's I guess I never updated this because I just added this. Its beta is actually, I think, closer to 30 on these, but at where we're at. But the point is that this will do 10 amps. This will only do like 6 amps. I thought it was, I guess it is 6 amps. But the thermals are pretty close to each other. But this will do 65 watts, and this will do 75 watts. So again, and the transistors are really cheap, actually. I mean, on Mauser, they're like, 55, 60 cents a piece. You buy 10 of them. In fact, I actually say that down here. They're 67 cents for 10. So, and two, if you're going to put current limiting, we're going to use this transistor just to be safe, even though, like I said, you could probably get away, for the the current limiting transistor, you could probably get away with with a TO92 package. But again, to be safe, I chose a fairly cheap, transistor that's suitable up to 1.5 amps, because they got to be PNP. Um, but again, it's better to be safe than sorry on things like this, and as like I said, as you're going to see, it's tricky to get to the it's next to impossible, without getting extreme, to actually get up to decent current and everything from out of these things. God forbid your fan fails, because these are going to need a fan for damn sure. But again, we can get our 2.5 amps out of this, and we get another half amp out of our regulator, so that gives us up to 3 amps total, right? So that's how we get our 3 amp specification that I outline up here at the top. So for the 7805, TJ Max is this, and I'm making these assumptions again just to be lousy with it, because a lot of people will actually do this. They'll actually use a cheesy heatsink on it and everything. Again, it'll help having some forced air cooling, because you're going to have it for the other part of it. You just are with this particular design. You're going to have it without having a huge heatsink. So if you have that huge heatsink, you might as well mount your regulator to it too, but you probably will have to isolate it then. You'll need a little insulator, electrical insulator for the heat sinking. But okay, so we've covered that, and basically, for R1, I'm calculating, just right off the top of the bat, what we need for, to have a current pass, or a current. I mean, this is the this is the R1. Okay, R1 is associated with Q2, so you can kind of see that on the simplified design up here. That doesn't involve a current limiter, but I'm calculating, and again, this is a place to start. You might have to tweak this in practice, because you don't know what your exact values are going to end up being, but this should be close. Since we only want to allow like half an amp through our regulator, I'm assuming that I want to kick this transistor in when the current gets above half an amp. So below half an amp, it'll just be the regulator, that's mostly supplying to the load. But above half an amp, it'll drop 0.7 volts across our 1.4 ohm resistor, not this resistor, because their design's based on 10 amps, which is almost absurd. With a single transistor, you're not going to get that. I mean, again, I'm pleased that this book even covers this. I've never seen this covered in a textbook, but Malvino in 8th edition does cover it, at least. Most textbooks never even mention this kind of thing, I don't think. But any rate, so 1.4 ohms, and again, a half watt resistor will be fine, because we're really not dropping that much power through that. So, and you'll probably have to build a 1.4 ohm up unless you want to get a precision device, but you can build it up by, for example, taking a 1 ohm resistor and then putting another couple of 2 ohm resistors in parallel and putting that in series with a 1 ohm. That'll give you 1.5 ohms. That'll be close enough. The point is that it'll kick in somewhere around there. But again, in practice, if you have a bigger heat sink on your regulator, yeah, you can actually have it handle more current. Like their example, they're actually having that regulator handle all the current. But, you got to understand something, that, these transistors, like Q2, the one we got, has a beta of about 30, okay? So, but since we're only going to pass 2.5 amps through it, like I talk about here, basically, that 2.5 amps, is going to be divided by 30, okay, for its base current. So, so 2.5 amps, divided by 10 would be 250 milliamps. So it's going to be just under 100 milliamps of base current required to turn this transistor on. All right, but that base current actually does feed through this, so you don't really have to worry about it too much. I mean, because again, it's going to come out through, and again, use this example. Let's ignore that for a minute, but it'll come out here and it'll go through here, so it's going to have to handle another 100 milliamps on top of what's going through this. So that's a significant amount of current there. That's like 10% of the rating of this thing. So it's going to have to handle that base current too. So, and like they say, you could maybe use a Darlington in there if that becomes an issue, and then your base current would be 10% or less of that. But you know, for the sake of argument, yeah, it's going to have to drop some of that current, the power of the transistor in through the regulator too. So, you just got to keep that in mind that it's going to be an issue. And like I said, I talk about these alternatives here. One of the alternatives is you could put more than one transistor in parallel with this, but you would have to put a little like 0.1 ohm ballast resistor on the emitters of each and every one of them, so that it mitigates their likelihood of any one of them being a current hog. Because if one of them fails, well, they'll all fail in quick succession. If you're got a short circuit condition or whatever, or even just under normal operating conditions, it can transfer an overload depending on how much of a load you got. So so it's good to have at least 0.1 ohms. I've seen some people use 0.3 ohms, and you can do that. It just increases the overhead. And since we got such excess voltage, you could put 0.3 ohms there as a ballast resistor and have more than one transistor and have them share the current. And that's one of the tricks, to get around the limitations I'm presenting in this example here. This example is based strictly on a single transistor. But the problem is, if you have multiple transistors, we got, instead of having 100 milliamps of base current, you had like 300 milliamps from 3 transistors going through that. So that regulator is having to handle that too. So, it might make more sense to use Darlingtons in that situation where you're trying to drive more series pass elements, because that's one way to get around these limitations. Because like I'm demonstrating here, and this here I got it 2.5 degrees centigrade per watt, so that's what I based it off of, and that's to get this rating, and it does require forced air cooling. But like if you went with a honking big, like 1 degree centigrade per watt heat sink, which again, be king of overkill, it's possible, especially if you make your own. I mean, you're going to spend a gazillion bucks on it, and then you still got your thermal properties, so you better make sure. Oh, and by the way, on transistors, before I get off the topic, if you did make them parallel, usually with a transistor, the collector is tied to the fin, right? So, so if you have a collector, of multiple transistors on the same heatsink, you don't need to thermally or electrically isolate them from each other, because the collectors will all be connected anyway. In fact, in a lot of situations, that actually comes in handy because it gives you a really low impedance output. So you can actually take your tap off the heatsink sometimes, if it's a big heatsink. If you're making like a welder or something with it, spot welder, you can kind of use tricks like that sometimes. So that is one less thermal resistance you have to worry about, even though you have multiple transistors on it. But this is one of the few cases where you can get away with that. But again, take a continuity checker and make sure you do that with your transistor. But it's almost always the collector that actually is tied to the fin. And just to make sure I'm not full of shit, I just verified that, so I paused the video. But yeah, on the TIP31, that's certainly the case, and like I said, I think that's pretty universally the case. But so it's that there's that. So it's actually pretty easy to parallel these, and if you do that enough, you can actually put out the same kind of current we're trying to put it out without forced air cooling. If you can just spread that load out, then you could actually go, like if we had 3 of them in there, even 5 degrees centigrade per watt, we could get 1.6 amp. Let's see, 8 degrees centigrade. So we could have an 8 degrees centigrade per watt heat sink, which, like I said, might be a 3 degrees centigrade per watt heat sink without forced air cooling. Then you got to look at the temperature rise though. So you got to do some different math there, because then you got to look at, okay, what's the case temperature of the device supposed to be, and then how hot's the heat sink going to get, with a given amount of power going through it. And you saw the heat sink graphs. So you can choose it for forced air cooling, but you're no longer dealing with degrees centigrade per watt, so this spreadsheet wouldn't apply. So, so you're kind of looking at temperature rise. So it's going to be the total temperature rise of what the, degree centigrade per watt of this thing will be, times the wattage, you're running it at. Okay, which, like in our case, we're going to be running 30 watts through the transistor, right, at 1.67, so you got 1.67, god damn it, 1.67 degrees centigrade per watt times 30 watts, because again, well, it's actually not 30 watts, it's 25 watts, because it's 2.5 amps dropped over 10 volts, because that transistor is going to have to drop 10 volts across it too, right? So, so basically, that's a temperature rise of 41 degrees. So if you take 150 degrees centigrade, which is its TJ max, as you see here, for a TO220 package, that's generally going to be true. Because you can see a TO3 package, usually will let you go up to 200 degrees centigrade for a TJ max. So, but those are considerably more expensive, and the TO247s are pretty good too. Some of them I think will let you go up that high. It's definitely higher than 150 for a 247, but again, those are more expensive parts. I'm trying to keep this cheap here, is what I'm trying to do. Yeah, if you don't mind, buying some more expensive parts, you can get a little better performance here, and we'll explore that. Like, for these same ratings here, I got 8 degrees centigrade per watt, right? So if one of these transistors, this transistor will barely handle an amp, but one of these down here can handle 1.7 amps under those same exact conditions. So that's the benefit of having a spreadsheet like this, and it turns red, if there's an issue. So, so it kind of shows you which transistors perform best, all at the same time. But at any rate, to get back to my calculations, so if you take 150 degrees TJ max and subtract our 41.75 degrees, you son of a fucking bitch. Calculators suck. Okay, son of a bitch. Okay, we're left with 108 degrees centigrade. So that's our envelope. Now we got a room temperature here of 40 degrees centigrade. So subtract that from 108.25 degrees, that gives us 68 degrees. So our maximum heat sink temperature rise, and this includes the thermal compound, can't be any more than 68.25 degrees. So if you go over and where the fuck, if you go over and look at that heatsink catalog, and let's say we're going to use this heatsink for shits and giggles, with no forced air cooling, basically, okay, we got 25 watts going through it, right? So depending on the model you use, I got 2 different models on here. Just take your pick. Let's use this one. It says that the temperature rise, at 25 watts, it'd be about 32 degrees or so. So, and that's centigrade. So we're well within our performance on this heatsink. But of course this isn't for TO220. But let's just look at this package though. It could be any heatsink you choose if you want to be creative about how you mount it to the heatsink. This won't quite go up to 25 watts, but you can see it on these graphs that it comes close, and you can kind of interpolate. So if you use the best heat sink here, you can assume it's going to be in the 60s. So this would be really marginal. We got 68 degrees. So so again, chances are good you could probably get away with this, but boy, it'd be close with no forced air convection. Now with forced air, you're fine. I mean, because then you can use the degree centigrade per watt, which is about approximately 1 here. So, but that's how you would do it if you were doing it without forced air. So, just FYI, even though I don't set my spreadsheets, because on these, when I made this thing, is when I was doing my power supply design. So, I was always intending on using forced air for the most part. Even though for lower current ratings you don't have to, actually. And if you want to put a fan controller in there, you could have it turn on, monitor the temperature right around your your part, like I said in the ambient discussion, what ambient temperature is, and have it, kick the fan on, if it starts getting, higher, and maybe even have it variable speed fan controller, so it's less noisy, and it gets noisier the higher the load, and that's always nice feedback to hear that fan speeding up. Okay, that gives you an idea. You're starting to pressure your luck on the power supply. The fan's getting louder. So it's kind of nice little feedback to have when you have that variable speed fan. But at any rate, the point is that with a single transistor, at 2.5 degrees centigrade per watt, forced air being assumed, and again, it shows you the graph, foot per second, and that's why it's nice having an enclosure, because you can kind of calculate, if you know the specs of your fan, you can kind of calculate how many feet per second you're going to have flowing through that. If you have a half a square foot wide enclosure and a fan at one side and a vent at the other, you can say, okay, well, I got a 250, CFM fan here, okay, and so that's going to put us right here at our thermal, conductivity. So, you would have to actually adjust your figures to that, but I always assume I'm going to make a whopping big heat sink and pull it off by hook or by crook, but you would have to adjust, for your actual airflow, your thermal capacity. So if we had this heat sink in 1 degree centigrade per watt, doing our 2.5 amps, 25 watts of power dissipation, and let's say we're using, this heat sink here at about 250 CFM, okay, I would have to use 2.5 degrees centigrade per watt, which is exactly what I got here. So this heat sink would actually work for our application with forced air at 250 watts. Now, faster the CFM, the more power you get. So if you get a 600 CFM or whatever, and remember, it's about, if you had a 200 CFM fan, that's cubic feet per minute, but a half a square foot profile, you're actually getting like 500 square feet per minute airflow. So, the smaller your case, so for the same fan, again, if I took a 250 CFM fan and actually had a 1 square foot, enclosure, a channel for airflow, again, as a rough rule of thumb, you can say it's going to, be 250, 250 feet per minute that are flowing, square feet per minute are flowing through there. If you cut that enclosure in half, it's 500. So, if you cut it in half again, to a quarter of a square foot, yeah, I mean, you can get up to 1,000 square feet and use this figure. But again, that's a really rough rule of thumb. In practice, it's risky thinking about that because it depends on the actual airflow by your component, right? And that's harder to measure, but you can, if you have a little anemometer, you can stick that in there and that'll give you an airflow rate. So, my point is that's an optimistic way of doing it. You cut that in half or so, you're probably in good shape. But if you just assume, like let's say we did have a quarter of a square foot enclosure, it's really safe for me to assume, that we'll have 250 CFM flowing through that. Even though in practice through the enclosure, it might be more like 1,000. But it depends on your performance because, your fan, might not perform as well. And, just ask a mechanical engineer what all the complexities are to this. And, but again, this is, for your test bench, not so you can design like aircraft parts or anything. So, but that just gives you kind of a primer of the problems you can run into. So, there are lots of considerations. I'm just trying to kind of walk you through it, but this is a detailed analysis of this whole thing, so keep in mind. But at any rate, so with our little transistor and our heat sink figured out and everything, okay, what the fuck did I do? Let's see, 40 degrees, oh, we got 8 degrees centigrade there, 2.5, for fuck's sake. Yeah. Put that 2.5 in the wrong place. Okay, screwed up my spreadsheet. Okay, so, but at any rate, we're up to our 2.6 amps, which is what I talk about in our little, what the fuck, annoying where, fuck you fucking stupid, ugh, I don't install that damn thing, That's not even part of McAfee. That's some kind of bullshit that when you install, fucking goddamn Adobe Reader, it always installs that fucking thing on there. That has nothing to do with McAfee. It's just a little adware thing from McAfee to try to scare you into buying their products. I already have their shit installed. So, anyway, although sometimes that actually does come in handy. Sometimes, for some reason, my virus software gets turned off, and that does tell me. So, so it's not totally useless. It just still kind of pisses me off once a week that pops up. But yeah, so anyway, like I said, so that's got our, our 2.5 amp thing figured out. And then for Q1, I start talking about, but at any rate, but that goes to show you the same rules apply, I mean, to the series pass transistor. And again, we're really pushing the limits on this. I'm not leaving any tolerance for error on this at all. In other words, 2.7 amps, this thing cooks itself. And you can even press your secondary breakdown down below, critical limits. Let's see, because here's our transistor here that we're going to use, and yeah, because I meant to cover this earlier, but you got this SOA curve. I've covered this in some other videos, but this only loosely has to do with power. It's rated for a TJ max at 150 degrees. But this is for 25 degrees centigrade. So this is not really a power graph. It kind of is, but it kind of isn't. But like, for example, in our case, we're going to be dealing with 10 volts collector emitter, right? And our amps is going to be like 2.5 amps. So that puts us right here. We're well within any SOA. And you don't have to worry about the dreaded secondary breakdown until your voltages get high enough. But again, if you're running things close to the limit, it's possible that even the secondary breakdown curve could end up moving down. If we're running it at a higher voltage and stuff like that, even though we think we're safe, but when we're starting to run too much current, it could really start heating it up and even move that, and you could end up suffering secondary breakdown because that's a thermal effect. Where localized hot spots punch holes in your, shatter your semiconductor basically. If it gets too hot, just because it's not evenly, the die's not evenly, it's not all the same temperature, so it generates hot spots, and that's what they call secondary breakdown, but it really is a higher voltage phenomenon. But anyway, but we're well within our SOA, and then you can come down here, and of course, you got your typical power to rating curve, like I discussed earlier. You can calculate your own thermals data off that thing. So, but, SOA is something, you really got to be worried about in transistors, just to make sure that, because this is the maximum power. You follow this curve, right? If you do the math, like 7 volts or whatnot, at 10 amps, that's 70 watts. Okay, there's a 75 watt part. So it's going to come out to about 75 watts, clear along this curve. The higher the voltage, 30 volts at 2 amps, and that's like, 2.5 amps, is, going to be in the, 70 watt range, right? So, yeah, I mean, this is, but it's only at 25 degrees centigrade. So if you're operating at room temperature, that's great. It tells you if you're in your safe operating area because it's based on the TJ max. Now, your other calculations are going to be based on TJ max too, right? So it's still valid to use this with that because it's based on the assumption that our junction temperature is actually going to be 150 degrees. And it will be, for example, in our current case. This will give us a junction temperature, if we're running it at a 40 degree ambient temperature, the actual chip temperature will be 150 degrees if you're putting 2.6 amps into it. So that puts it squarely along this curve. And again, so we know we're going to be less than TJ max no matter where we're at on this curve. But I'm just saying you cannot use this graph as a power calculator. Don't think you can. It really is for a safe operating area in terms of collector current versus voltage drop across the transistor. It's not for trying to use it for power purposes as a way of cheating. You've still got to go through the thermals. Again, this is based on 25 degrees centigrade. That's only valid at 25 degrees centigrade. But again, it's still very useful because of the TJ max. It doesn't matter what temperature we're running out. If you've already done your thermals, you can certainly look at this and independently, of your thermals and say, well, in fact, this is one of the first things I always look at, really, is the safe operating area curve when I'm looking at power transistors. But in our case, again, we're right in here, well within the safe zone. Okay, but don't think that, oh, well, hell, this is with no transistor, no heat sink on it, because this is with no heat sink on it. This specifies the case temperature, TC, equals 25 degrees. This does not account for heat sinks. So you may look at this and falsely think, oh, hell, I don't need a heat sink to run this thing. No, you do. Okay? You don't if your case temperature is 25 degrees centigrade. So again, if you got it like, in the middle of the winter or something, maybe it will be. But, or got a refrigerator on the damn thing, but the fact of the matter is that no, it just helps you make sure you're not going to exceed the limits, especially when it comes to voltage. Because that's the key reason they have this here, mostly because this secondary, the solid lines are the second breakdown curves, right? So mostly, when you start trying to use these things at higher voltages, you're limited by secondary breakdown. Like for example, at 50 volts, you may think, if this curve kept going this way, you may think you could do, over an amp, right? Well, no, you can't. In fact, you're limited at DC current. You're limited to only less than half an amp, with this transistor, if you're trying to put 50 volts across it. So, and that's a cardinal rule. That's by the breath of God. Okay, do not exceed that curve. It takes less than 10 milliseconds to destroy your transistor, and that's what'll happen. That secondary breakdown is that's real shit, and you really got to watch out for it, because that's outside of your thermal calculation is not going to reflect that. You may think, oh, well, I can do, X amount of current because the thermals say I can, because this is the thermal curve right here. This is what we're calculating is the thermal curve. Okay, but like I said, if our voltage were high enough, this isn't going to tell you your transistor is going to blow up because of secondary breakdown. You have to refer to these curves, and you should immediately do that after doing these calculations if you're dealing with higher voltages. But again, that's why this is always the first graph I look at on a power transistor, see what its secondary breakdown limit is. And here, it's, about 36 volts, is where it starts to deviate. But if you're running it at 36 volts, like I said, if your thing gets hot enough, you may be pushing it into secondary breakdown territory without knowing about it. So my advice is stay well clear of it. So that really limits, what you can do with these fucking power transistors, because, it limits to about 30 volts. And that's pretty common. And, all transistors, because of their size, power transistors pretty much have a secondary breakdown problem, even though this curve isn't always published, especially in audio devices. So, don't ask me what the theory behind that is, but, in a lot of audio transistors, you don't really see a curve like this, especially the older ones, which I have some of, lying around, TO3s, but their data sheets have shit in them about stuff like this. So, anyway, just FYI, you won't always see one, and with a power transistor, really proceed with caution. I would definitely ask some people on forums or something, electrical engineer stack exchange or some shit. But at any rate, so basically that gets us, our transistor here, figured out, and then I start dealing with our little, bypass here, which I explained earlier. This tends to divert current away from our transistor and through the device, so that the device itself can, if there's an overcurrent situation, it makes the device's own thermal shutdown kick in. So it's using the regulator itself as a safety mechanism. It's extending the natural built-in safety protection that these regulators have for overcurrent, mostly overheating, but also overcurrent in particular. And it's overcurrent they're extending into this, but it'll be the thermal circuit that kicks in and shuts it down, right? But if it shuts down, the whole thing shuts off, because that shuts, you know, the transistor off. I mean, there's just no way for it to power with this thing being dead, being shut down. But yeah, it diverts current away from this and into this, and like I said, it doesn't need much diverted through it to cause us to go into thermal shutdown, because we're already running at half an amp, right? And in a practical design, again, you use a better heat sink. You might be running at 0.8 amps or higher, right? So it won't take much to actually put this into thermal shutdown. So, in fact, you can try to run it at full blast if you want, but I'd rather this pass transistor kick in sooner than later. So if I was doing this for real, I mean, I would do like a point, set it to about 0.8 amps or so through the device, and with a slightly better heat sink. And since it's going to be probably forced air cooled anyway, that's fine. It's actually easy to do. So, but again, I just wanted to illustrate extreme case here so that we can concentrate on the transistor, and to show you how difficult it is to actually get any kind of real current out of it. Because like I said, yeah, you can use a better device at these same specifications, and I can get, like out of one of these 200-degree centigrade per watt deals. Unfortunately, I don't have like a, one of the bigger brother of this, because it'll have better thermals. I don't even have a 3055 in here for some stupid reason. But anyway, with these transistors, you can see some of these things can do, at those same specifications, you'll double the current, owing partly due to the fact it's got a better, a higher TJ max, and it's got lower thermals because it's a TO3 case. So, a TO3 heatsink, of course, is required. Those are a bit more of a pain in the ass. And again, if you're careful, you can mount a TO3 to a heatsink directly, because like I said, if you had, without a mounting kit, you can do it. You just got to over drill your hole size on them a little bit, and then be very careful about your screw placement. But you can do it without mounting hardware, especially if you don't need an insulator. But insulators for these things are pretty cheap to buy, so you can still put an insulator in there, but use them without a mounting kit. I hardly ever use those. Just make sure my holes are big enough to where nothing's going to come in contact with it, and then you can solder your wires to it, and to the actual pins, and you're in pretty good shape. And there's other ways of doing it, but anyway. But the point is, this could, if you're doing with a TO3 package, yeah, you could handle about twice the current with the same sort of heat sinking involved. So so that starts to become more practical, because you can make this thing even higher current, which is another way of doing it that I didn't mention in my alternatives up here. I didn't mention, using just a bigger transistor, because you can do that. And again, those TO247 transistors, are likely going to have at least 175C. I can't remember what the actual specs on them are. But again, they're way cheaper than TO3s, although I will tell you, you can get some pretty decent TO3 transistors off Jamico. Some 2955s for like $250 a piece. Excellent deal. Although I guess I need to buy some in case there's a big rush on them after me mentioning that, because it's kind of a little secret. Because if they get more popular, I'll probably try to up the price on them. But at any rate, you can find some good deals if you know where to look around sometimes. And those will be the real deal. So in all likelihood, although Jamico can be screwed over too, because they do get a lot of stuff from China, but they're they've been around for a long time. I mean, they were around when I was first into electronics, and I fucking found out about them by by seeing them on in catalogs. I mean, in electronics magazines. So like one of the first vendors I ever did business with back in the early '80s. So but yeah, you can find some good shit on here. So, sometimes better than others, but sometimes their stuff's pretty interesting. I mean, like I said, they got some regulators, and this is a regulator here, a 337, I think, for $545, which is a pretty good price. Yeah, it's the I guess it's the negative regulator version of the 3017, but I guess it only goes up to 1.5 amps, but this is probably going to have better thermals. You know, because you can just buy a more expensive fucking regulator too. I guess that's another option. And again, they have them in higher current, but again, a lot of times they're still going to end up with lousy thermal thermal specifications. Let's see, 200 watt or 20 watts rated power dissipation. I don't know. That implies that might not be the best deal. Maybe that's why it's as cheap as it is. Yeah, don't really see. Oh, here we go. Yeah, thermal resistance junction to case 12 degrees centigrade. Oh, okay, for a K package. That's probably the K package we got here. Yeah, it's max is so it's 2.3 degrees. That's pretty good. It's about twice as good as what an average TO220 regulator will be. But anyway, it's still way more expensive though. So compared to 3017 or 337. But anyway, the point is though is that we can get some good alternatives there, with heftier power transistors, then we could actually pull it off with the same exact specifications. Now, let's say we went to 1.5 degrees centigrade per watt. Okay, then this thing can put out, like these generally can put out 5-6 amps easily, and even our transistors could actually fully handle the 3 amp load. And in fact, if we wanted to make this regulator into a 5 amp regulator, we would have to, even if we went down to 1 degree centigrade per watt, you still couldn't do it. Although if you put 1 amp through the regulator, you kind of could, so you could actually just barely pull it off with no tolerance for error. And again, I don't like having low tolerances for error, because even this design we've been discussing, for fuck's sake, even this design we've been discussing, there's almost no tolerance for error on it. So, I do not like doing designs with low tolerances for error, because shit happens. I mean, your capacitors dry out and your electrolytic filter caps dry out, so the capacitance decreases. That's why I didn't mind looking at 47 millifarad, because theoretically I'd use a much larger value of capacitance for this circuit, especially when I was trying to get 5 amps out of it. I'd use a minimum of 10,000 microfarads, but probably 15 or more, would be warranted, because again, they age, and you don't want your power supply start getting more and more ripply with age. So, but again, dust gets on your heat sinks, even with forced air cooling, your heat sinks get dusty inside there. That affects how well they cool. I mean, it can really, depending on how thick that dust layer, it doesn't have to get too thick, before it starts really seriously degrading the performance, because that's an extra little barrier there. It's like putting an ever thick growing in thickness fur coat on it. So, so there's that, and other parameters. So it's always good to have safety factors, just because shit happens, and you don't like to play it too close. So, on your specifications, you don't like to make too ambitious of a design, too many, you always want to assume worst case on a lot of things. So, even if it's just for your own bench, it's a good idea. You don't want your precious circuit you spent hours building burning up because of a bad power supply choice. But like I said, bigger heat sink is recommended. Let's see, suitable TO transistor may work. Okay, but yeah, I was talking about the the bypass circuit here. So like I said, the good thing is that I chose a transistor that would be universally acceptable for all bypass circuits. So, this I think I mentioned it earlier. Where the fuck did it go? Q1. Okay, yeah, the BD136. That's a fairly cheap little transistor, and up to 1.5 amps. That'll more than handle this. So, in any circuit you build, even for a 317 regulator or whatever, you can always use the same exact bypass circuit and the exact same, Well, the resistor values, would depend on, of course, what kind of current you're getting out of it, because you got to size this for your current. And in our case, I don't even know if I adjusted this. Let me see if it's 'cause I don't know if I made adjustments to this or not. To adjust for the maximum current limit. Because originally I tried, doing a 5 amp supply, but I just thought, man, that's just going to be too ambitious. So I had to dial it back to a 3 amp. So that's why a lot of stuff was actually set up originally for a 5 amp. Let's see. But at any rate, for fuck's sake, rather than reading through that damn thing, basically the resistor value, we want this to, short circuit, okay, it's 2.5 amps going through our transistor. Because this isn't the overall, the transistor itself is what we're worried about protecting. The regulator protects itself. In fact, you're just going to use the regulator to protect the transistor by causing the regulator to shut down by diverting its current into it. That's the whole idea. But it's a transistor, the current that we got to size this to. So it's 2.5 amps. We want it to trigger, again, it's base emitter voltage. Diode is going to be 0.7 volts. So it's 0.7 volts divided by 2.5 amps. It's about 280 milliohms. So basically, yeah, you need to size this for about 280 milliohms, and 4 1 ohm resistors in parallel will get you close enough. That'll make it shut down at a little higher current though, but that's, again, since we got so little tolerance of error, you may want to make it lower, but so you'll just have to come up with a creative way of doing that. But this has got to be able to handle a lot of power, but it's not going to drop much voltage. So so we got 2.5 amps going through it, but only at 0.7 volts. So it's about a 1.75 watt resistor you're going to need at least. So again, if you use 4 half-watt resistors, that gets you there. But you may still end up having to put a smaller resistance in series with it. You can use a suitable piece of wire to do it. In fact, if you don't mind having coils of wire, you can just use copper wire, like 22 gauge or something like that, and just use its own resistance to get up to 280 milliohms. That's one way of doing it. So, but you can definitely put like 4 resistors in parallel, and for like 5%, you may get lucky and have it be 280 milliohms, but if you don't have a milliohm meter like that one I showed you on eBay, you'll have maybe a hard time measuring it. So that's where it becomes an issue. So, but again, that's why if you use wire, it's pretty safe, because it's by the length, okay, so you can calculate how many ohms per foot it has, etc., and just cut, use a ruler to size it to the length, and you'll probably be fine. But it's nice having that assurance of using actual resistors. So again, just throwing some creative ideas at you, so there's different ways of going about it, but you'll probably have a hard time measuring 280 milliohms with an average ohmometer. Even if it does give you a reading and you think it's giving you a reading, like one of those little gizmos off of like one of these things, it's supposed to read down to low resistances, but it's not reliable. I mean, so, my point is that, if you think you're getting that reading, you may not. So it's better to buy resistors and try to cobble them together, high precision resistors or something like this. But just keep in mind, it needs to be, 2.7 watts or so. So, and if you use wire, its resistance will change, of course, if you get too much current flowing through it. So, use a suitable size wire with 2.5 amps. Again, 22 gauge would probably do you without too much of a temperature rise. And you could always run tests, right, and see if the thing fucking actually shuts off, but of course, without cooking your transistor, I don't know. But just the point is coming up with that value might be a little tricky, that 280 milliohms. And again, you may need to adjust it too, but you can't really just stick a potentiometer in it. It's too many watts. Okay, and again, you're going to have a hard time buying a 1 ohm potentiometer. Really, I don't even know if I can't remember if they sell them that. I'm sure you can buy them somewhere. I don't know how much it'll cost you though. They might come run a premium. I'm not sure. You can look into it, but if you can find one, again, you can't look at the wattage rating though. You got to look at the current rating. So so if you had a 1 ohm potentiometer, how many watts might you need? You need, let's say, a 3-watt potentiometer, right? Let's see, I squared over R, so R is 1, so it's going to be 3, so radical 3 is what we're looking at. Alright, so it's about 1.73 ohms, or amps. But that's still, so a 3-watt potentiometer can't deal with more than 1.73 amps. You'd have to get a 5-watt potentiometer, and it's going to be a panel mount potentiometer. It's going to run you some money. So, probably cheaper just to try to cobble together fixed resistors, because you really usually won't want to vary it. But if you did want to vary it, and you might want to, you'd probably need a half a watt potentiometer. So radical 5, gives us 2.2 amps. Even a half watt potentiometer is not large enough for this on its own. So just be aware of that. You still couldn't even handle it with something like that. You need a even bigger one. So, but it can come close to it if you also had a resistor in series with it. Maybe you could do it, but I mean, it still can't handle 2.5 amps. You'd have to lower your output. Your cook your potentiometer, and if that gets cooked, well, then you're gonna have no current protection anymore, or the thing will shut down, because all your current's got to pass through the goddamn thing. So, but at any rate, that pretty much kind of covers it all. I mean, again, you can kind of read through my notes. Again, we deviated a little bit from this, but I talked about using Darlingtons earlier. No, well, I guess there's the one obvious thing I need to cover, and that's up here. The alternatives. Again, we already talked about using parallel transistors and so forth, and we talked about using a bigger regulator as an alternative, and we talked about using whatever else we talked about. We talked about using bigger transistors too, more powerful transistors. But there's one other option, and this could help a lot too, but it depends on your power supply and what else you're doing with it. Like, for example, in the power supply I mentioned, that we're working with, you may not just have a 5-volt regulator on it, but you may have a 12-volt regulator on it too, right? That maybe it's just doing 1 amp, right? So, you can probably get away with that, under the circumstances, if the ripple from your 5-volt regulator doesn't, start causing it a lot of noise problems that are unacceptable to you. And oh, by the way, too, on these regulators, these 3-terminal regulators too, you can increase the voltage of them by putting like diodes, in series with its, sense terminal. So, you can raise it from 5 volts to 5.6 volts by putting one diode, 7.2 volts by putting 2 diodes, or putting a Zener diode in there. You can raise it up to whatever voltage you want. In fact, these 3-terminal regulators can be used in a lot of ways that a 317 is. You can set them up as a constant current source, just like you can a 317. You can do a lot of this same stuff with it, just keeping in mind that instead of it dropping, 1.25 volts across it like a 317 will, it'll drop 5 volts across it. So you can set it up as like a, constant current battery charger, but instead of it being, a 317, you're setting it up with 5 volts, you'll need a larger voltage, but you can use them for things like that, believe it or not. You can even make it adjustable like you can a 317. So it's just you're dealing with a much larger voltage drop on it, so it can't drop down to less than 5 volts. But you can do things like that with these regulators, by the way. But at any rate, so if you might want a higher voltage, right? Like a 6-volt power supply or something like that. Well, you can do that, and we got enough headroom on here where you can make this thing 6 or 8 volts, and guess what happens? That makes your thermal performance increase, because let's say we did do that, instead of 5 volts out, we still have the same 15 volt max, but if we had 8 volts, okay, and let's go back to our original heatsink here. So you can see that instead of 5 volts, we're stuck at 2.6 amps out of our transistor. If we did 8 volts, because we're operating at a higher voltage, they do have 8-volt regulators too, by the way. I got a bunch of them. But now we can get to 3.7 amps with our transistor. So just from that one change. So, and the same heatsink and so forth. So I mean, like I said, there's advantages, but that brings us into my next point, which is one way you can improve the performance here is by reducing that overhead voltage. One way of doing that is by having a higher voltage output from your regulator. Because your regulator, it's only worried about the voltage. It's not worried about the voltage it's supplying to the load. That's not what dissipates power. It dissipates no power, for 5 volts or less. What's going through your load, the regulator doesn't care about. It's your load that's dissipating that power. It cares about the voltage above your load. So in our case, from 15 volts down to 5 volts, that's what it's concerned about. That's what your regulator's worried about, is what it's going to do with that power. So your load dictates the current, but that same current is flowing through your regulator at this big voltage difference. That's why it dissipates the power it does. If you could do something, and again, one way is by increasing the output voltage, to your regulator. Like if you made a put a 9-volt regulator in there instead of a 5-volt regulator. Well, look, we can do fucking 4 amps with these same exact specifications with that same exact transistor now, because we're dropping less voltage. Okay, and like I said, if you put a 12-volt regulator in here, you're pressing your luck, because a 12-volt regulator from a 12-volt transformer, you're going to have a hard time operating it, especially with pass transistors. You're running into the same problem we are with 5 volts, and why I couldn't really drive a 5-volt regulator, boosted regulator like this off of a 6-volt transformer. It's because you're running into the same problem, with ripple and everything else with 12 volts. So you really need like a 14 or 15 volt transformer to drive a 12 volt power supply with any current at all. So, you'd have a hard time boosting a 12 volt supply. So, son of a bitch. But yeah, but at any rate, like I said, boy, you can get 8 amps out of that, except that you gotta, add a few extra volts to it for the overhead. You just got to. So, so instead of 15, it'd be like 18 volts. So if you did that, you'd be back down to the 4 amps. Again, that's why I have these differentials over here. It's convenient when you're doing power supply design, especially when you're looking at variable power supplies, because those transistors, it's easy to make a variable power supply with transistors until you're setting your voltage really low. That's when it's hardest on your pass transistors, is when it's having to drop more voltage. So that's a little secret that, like a 317, you have an easier time getting power out of a 317 when you set the voltage high. So let's say you had it, a 40 volt input to a 317, so it could vary from 0 to 35 volts, right? Well, you're going to be able to get more current out of it, if it putting at a higher voltage, like 30 or 35 volts, because it's not having to drop as many volts. It's having to drop 10 volts. But if you put like 5 volts out of it, with that, then it's having to drop the difference between 5 volts and 30 and 40 volts. So it's like 35 volts. That's way more power if it's like at 1 amp. Okay, so instead of it, dropping, like 30 volts as the output, it's dropping 10 watts. versus 35 watts, you know, when it's at the lower side. That's why 317s, if you're trying to make a high voltage supply with them, it's really, really difficult. You end up with, you know, getting like 200 milliamps out of it, full range. So just FYI. But at any rate, back to our discussion here, you know, where we got a 5-volt supply. The other thing you can do is you can use some power resistors in there to eat up some of that differential voltage. You know, because frankly, we don't need any more than 5 volts to work with, you know, as long as it's below the ripple and everything. So, you know, you can, and this is done, you know, you actually, I've seen this done a lot, where you just put, you know, we can just eat up, you know, so instead of having a 10 volt drop, we can eat up half of that voltage pretty much, you know. So you know, so basically we end up with a 5 volt drop. You just use a big power resistor, you know, for the whole circuit, you know. So if the input, you know, to our circuit down here, you know, you end up with you know, we got 3 amps max going through it, right? So that's how you size the resistor. You size it for the maximum current. So at 3 amps, we want to drop 5 volts, so you know, you need about a 15 ohm resistor. You know, for dropping 5 volts at 3 amps, yeah, 15 ohms. So you need a 15 ohm resistor, but a 15 watt. Well, shit. No, you don't need 15 ohms. Well, yeah, you do. I mean, 5 volts divided by 3 amps is, yeah, this fucking calculator, goddamn calculator. Okay, no, it's 1. I thought that sounded weird. Yeah, 1.66 ohms, you know, is what you need, all right? But you need it at 15 watts. So, you know, so you can buy 1 ohm resistors off Amazon for like $5 for 10 of them, you know, that are like 10 watt resistors. So, you know, for example, you could use, you know, one ohm resistor in series with 2 parallel 1 ohm resistors, you know, and get your 1.5, you know, get you 1.5 ohms. So 1.5 ohms times 3 amps, you know, is going to be about 4.5 volts. So that's good enough. So let's put 4.5 volts in there. You know, in fact, I'll go ahead and just set this down to 0. So we got 5.5 volts dropped, you know. Motherfucker. Okay, so yeah, you got 5.5 volts dropped across the damn thing, because the resistor is eating up 4.5 volts, and so with everything else being equal, now we're getting 4.5, you know, 4.7 amps out of it, because we're not dealing with as big of a load, and even our regulator you can easily handle more current with. So, you know, you could actually get this whole thing to put out 5 amps just by making that change. So, you know, again, you got to look at, you know, make sure your ripple voltage and so forth, you know, is still out of its operating area range with doing this. But the point is, it is a simple trick, you know, to try to eat up some of that voltage, you know, so your regulators and so forth don't have to deal with it, right? So, again, you may have to use larger capacitors, and, you know, which you should do anyway. Again, you know, larger than the, you know, especially for a 5 amp supply, you'd want to use, you know, 20 millifarad or more, well, 10 millifarad or more, but preferably 15 or 20, you know. So, but you can use smaller capacitors in parallel to do that. But, you know, the point is that, you know, you want to make sure your ripple, you know, is still out of its, you know, its dropout zone. And that can include the transistor too, you know, because the transistor will probably add another volt to it, you know, to your dropout, you know, especially with your little, you know, your little current limiter and everything in it. So, yeah, but I'd expect it to, you know, be 4 volts or so, you know, 4 or more volts. So I wouldn't want to drop more than 5 volts this way. But that way, you know, if your current's lower, the resistor drops less voltage and it's less of an influence. So, you know, but at any rate, I think that pretty much covers the gamut of running a bypass, transistor. It's not as simple as these data books make it look, and the sheets, because in a real world scenario, it's really hard to believe just how limited your options can be sometimes, and how hard it is to actually make a simple 2 amp regulator, or 1 amp regulator into a 2 amp regulator. Again, the first thing I would try, if your requirements aren't very stringent, is putting, again, ballast resistors on the regulators themselves, because they're pretty cheap. Like a 5-volt regulator, if you wanted a 5 amp supply, we'll put 5 of those in parallel, and, just use a pretty good heat sink. Buy yourself an 8-volt transformer, is the only other suggestion, because you can do that. You can, they do sell 8-volt transformers, but I'm assuming you're probably using something out of your junk box or something you salvaged. Because transformers still aren't generally too cheap. So anyway, but oh, by the way, in fact, this is another great thing about Jamico. Not affiliated with them, but they do have a really decent selection of power supplies, and that includes wall warts and everything else. Let's see, that's like a big thing they focused on starting 20 years ago. And they do have a clearance center, which a lot of times you can find some pretty good deals in their clearance area, for all kinds of shit. But yeah, they do have a huge assortment of wall warts and stuff like that, and a lot of it's surplus stuff. Even though Jamico does sell new stuff, but they also have some, oddball stuff too. That's what's kind of cool. But power supplies and wall adapters, this is the go-to place if you want to buy adapters. I mean, I almost always buy my power supplies from here, although, again, definitely check Amazon too. In fact, Jamico actually does have an Amazon store. For some of their stuff, you'll pay more for it than going through them. But the only thing that sucks about Jamico is they don't have free shipping. And they do have like a minimum order, like $15 or something like that. But, so I tend to not order from them until there's enough parts to kind of balance out the shipping. I don't want to pay another $8 or $10 for shipping. If you live in California, it won't be as cheap. If you live in California, they actually have a store you can walk into. In San Jose, I stayed in San Jose, and I forgot all about it. They're just like down the street from me, and I really wanted to stop in and see their store since the early 80s. They have an actual retail store. So, or at least they used to, and they've closed it down by now, but I don't know. I doubt it in Silicon Valley like that. But anyway, it's especially if you're looking for oddball stuff. Because like I said, their catalogs were always wonderful. I don't know if they do print catalogs anymore. I don't think they do, which is a shame. Because their catalogs were actually easy to find shit in. Their search engine kind of is on the sucky side. But yeah, they used to have a catalog, and I guess, I think just a few years ago they stopped publishing them. I don't think you can get catalogs from them anymore. That really sucks. Because their catalogs are something to behold. That was always my toilet training material before I started reading textbooks on the toilet. Before it came real toilet training. But yeah, I'd always thumbed through Jamico catalogs when I was younger, and but at any rate, you can find stuff. It's harder to find stuff here with the internet, than it is in their catalogs. Their catalogs weren't very thick. They were always like 120 pages or something, but they're in full color, and they were just wonderful catalogs. I mean, wonderful, wonderful little catalogs. So it's just a shame they don't put those out anymore, as far as I know. Boy, they used to. And they used to have a PDF version of it, but I don't even think they have that anymore. So, yeah, I don't really see any reference to their catalog. So, who was Gary? Anyway, the fact of the matter is that, yeah, I wish I still had a fucking catalog. I was hoping they'd find one. Mail, fax, order, RMS. Because even if they had a PDF catalog, that's definitely way better than their search engine. Search engine does suck on this. Need to send them an email about that, pointing it out, because they could definitely use some improvements. But anyway, that's enough on the subject matter. But But they do have a lot of good power supplies, including from Meanwell and switch mode power supplies. Like this, for example. Which are halfway decent. But again, Amazon is still a big source too, but especially for wall warts. Because you got, I used to buy a lot of non-regulated wall warts, and then they got regulated ones, with switch mode, but then they got the analog, linear ones, and they have a broad selection of stuff. It's especially in the catalog, it was really great. In fact, fuck. Yeah. Yeah. I happen to have an old Jamico catalog sitting here, so it's got some water damage on it apparently, but yeah, I mean, this is the kind of catalog they used to produce. So, but yeah, they'd have just, like I said, all kinds of cool shit in here. I mean, they're just really nice little catalogs. So, here's an example of some of their power supplies, wall warts and stuff like that. And they have, open frame power supplies, and I mean, they're just really nice looking. I mean, I grew up with these catalogs, and this one's from 2003. So, but I know they were producing them up to like 10 or 15 years ago still. But I guess they don't publish them anymore. The pages all stick together as it got wet. Fucking leaky roof. But yeah, they sell all kinds of shit, they still do, it's just, it's harder to find on their internet website, so, but yeah, I mean, they were always my first go-to source looking for things, but that's less so these days, because I don't know what the fuck they have, because their internet search engine sucks, it's just, it's at least they make attempt at organizing it, and they're one of the better organized sites, I guess, but still, it just pales in comparison, because it's just not the same experience, and it's not as easy to locate what you're looking for. So, or to even tell what all they have. It's really hard. This is a good effort. Their sorting system here, but you can't sort by multiple items, and there's just a lot missing from this compared to like some other sites that you would expect to have. I don't know, just more control, like Mauser, for example, a lot better of a search engine. When you get to their shit. So I could definitely use some improvements, but anyway, but you might give them a look. Keep them in business, because it'd be a shame if they disappeared. But anyway, I think that pretty much covers it and wraps it up. This is a really long video, but at least I covered this in depth so you get some idea what's involved in doing these kinds of things. Because this is surprisingly difficult. Something you'd think would be so simple, because again, you see these circuits like everywhere in every data sheet, etc. But actually implementing them is really, really challenging. It's way more challenging than you'd think, especially given some of the power supplies I designed. But it would make me pull my hair out. Why can't this be simple? With using it in a practical situation with off-the-shelf transformers that I have lying around. If I want a little 4 or 5 amp, 5-volt supply, or 8 volt or 12 volt, I mean, it shouldn't be this difficult, but it is. It's surprising what the limitations of these power transistors actually, how they corral you into certain design choices. So, at any rate, I hope this is informative to you. I know it probably put you to sleep, but you probably didn't listen to all of it thoroughly, but I do my best. So, cheers. By the way, there is a version of that circuit that involves NPN transistors, that I saw in one of the data sheets. I can't find it, but, this, instead of PNPs, it does use a PNP transistor here, but the main pass transistor is an NPN. But this does not have current limiting. It's using this transistor in order to power this transistor, so you still have to add a current limiting circuit in here somewhere, otherwise you'll still blow your transistor out. But it is possible to use NPNs instead with a regulator. Now, if you're using a negative regulator, you could use an NPN the way we discussed. And I wanted to say too, there is not going to be a part 2 to this video like I talked about earlier. This covers everything I basically know about this kind of shit, without going into the rigors of making variable power supplies and all that crap. You know, even this stuff I had to spend all morning yesterday trying to remember what I did, because it's been like 2.5 years since I've done any of this. So I had to try to recall the tricks. It took like 9 or 10 hours for me to recall everything. But yeah, like I said, this is still basically how it's typically done. So, at any rate, that does wrap it up. So, cheers.